Hi everybody, I hope you're doing well. In this video I'm going to work session 14 question 6. But before I get started, I just want to put things in perspective. Chapter 14 is a kind of an intense chapter, right? There's a lot of data to analyze. You have to think about the rate law, reaction rates, integrated rate law, and we don't really have the opportunity to meet in person or run any sort of kinetics experiments. So if you ever want to chat about kinetics with me over Zoom, please let me know. If you're feeling overwhelmed or confused, don't be afraid to ask questions. But what I challenge you though, when you're working through the lecture notes and studying them and kind of redesigning maybe your own study guide, and then working through problems, practice as many problems as you can from the work session and the textbook, is that you'll need to organize your thought process. Really focus on what's given in the problem, and then how to tackle that problem, how to process that data. And I always like to think of kinetics, like even though you're probably not going to run kinetics experiments in your future career, I like to think of this chapter as a way to help fine-tune students' problem-solving skills. Because many of you want to be doctors, physician assistants, and engineers, and all sorts of great scientists. And it's important that when we're approached with a problem and some data, that we follow the scientific method in terms of developing a hypothesis and a plan and testing that plan. And so that's exactly what you're doing here in this chapter. So a ton of data analysis, but it's all within your means. Like, you can do this, but while you're studying, like I said, be very organized in approaching each problem and compare and contrast problems. I always found that really helpful. So it's like, you know, on the lecture videos, I worked question 5, and that's an initial rates problem, and I can show you in a second. And then I'm going to do question 6 here, and it's like, okay, I was given different sets of data, so I had to approach this problem a little differently. Why did I have to approach it differently? What was different? What was similar? And so that's going to be your goal for this chapter, so that when you do take the quiz, you don't feel overwhelmed and you like see all this data and you're like, oh my goodness, how do I even get started? You're like, okay, I know what type of problem this is. I've seen, like if it's a patient, right? I've seen these symptoms before. I know what tests to run. I know what formulas to use, and then let's check the results. Okay, so I just wanted to kind of put things in perspective here. And then the big thing also too is make sure you're connecting the concepts I'm teaching in the online videos to the word problems as well. Like, always try to, you know, connect it to the bigger picture, because everything in chemistry kind of builds upon itself. And so it's important that you're not just memorizing how to do the problems, but you fundamentally understand them, and then on a conceptual level as well. All right, so let's go ahead and get started. So in this question here, we're looking at the decomposition of dinitrogen pentaoxide, and we're provided the time and then the concentration of that reactant at a specific point in time. So basically, we're measuring the concentration as it's decomposing over 200 seconds, over a certain time period. This was different than the question I had worked in the online videos, where I'd given you the concentration of reactants, but the initial rate was measured, right? And so this was an initial rates kind of analysis. This is a little bit different here. So like I said, compare contrast as you're studying, make notes, you know, in your study guide or as you're doing problem solving here. So anyways, okay. So in this case here, because we're given data, we learned that specifically we studied 0, first, and second order kinetics, and that if we have the concentration of the reactant as a function of time, we can plot the data and figure out what type of kinetics it is following as it's reacting, okay? And so this table is provided for you on the quiz. You'll see that on the practice quiz. Definitely take the practice quiz. I think that will be useful for all of you. And so what I'm going to do here is I'm going to plot the concentration versus time. If I get a straight line, then that means that dinitrogen pentaoxide is following 0 order kinetics. When I plot the natural log of dinitrogen pentaoxide versus time, if I get a straight line, then it's following first order kinetics. And then if I were to plot 1 over the concentration of dinitrogen pentaoxide versus time, then that's second order kinetics. So I'm just plotting a lot of data here. So let's go ahead and get our Excel. I already typed in the data that was provided within the problem itself. I'm going to say equals natural log, and it is not liking me today. Let's see if I can get rid of this real quick. Delete. There we go. All right. So this is the natural log of the concentration. So always labeling to make sure it's correct. And then I also wanted to see if it's following second order kinetics. So I'll plot 1 over that concentration. So equals 1 divided by, there we go. And it just fills it all in for me. I've created a table, so that's why it does that for me automatically. If it doesn't do it automatically for you in Excel, you can just copy and then paste it and it will fill it in for you. All right. So the first thing I'm going to do is I'm going to insert chart, and I'm going to do an XY scatter, and I'm going to right click and select data. Now sometimes Excel will do the data for you. I delete it all because sometimes it chooses the wrong X values and Y values. So be mindful of that. I like to just, like I said, start over and select the data. I right click, I add a series, and I'm just going to do zero order kinetics first. So I'm going to choose the X values. So if I wanted to plot X, I need to select the time column. So I'm going to highlight time. And on the y-axis, I should plot just the concentration as is. And what you'll see here, and I'm going to see if I can I'm always like, okay, here we go. There we go. Zero order. I just want to make sure we have these all labeled here when we're analyzing them. So zero order, we have time in seconds on the x-axis, and then the concentration of dinitrogen pentoxide. I'm not going to make it pretty and do the subscripts because that will take too long, but anytime you're plotting data, make sure it looks pretty. All right, and then what I'm going to do is I'm going to right click and add a trend line. And I always go to options and I display the equation in R squared value, and we'll talk about that in a second in the chart. All right, cool. So I'm going to do the same thing for the first order. So I need to plot natural log of the concentration of the reactant versus time for this one here. So I'm going to right click, select data, add a series, my X values, time, my Y values, the natural log, the concentration. All right, this is if it were following first order kinetics. We have time in seconds and the natural log of dinitrogen pentoxide. And don't really need this here. Once again, I'm going to add a trend line, right click, display equation, and R squared value on the chart. And that's that one here. And then I want to see, does it follow second order kinetics? So I would need to plot 1 over the concentration of the reactant versus time. So insert chart, XY marks scatter. Where'd you go chart? Oh, I think I'll try again. Alright, so then I'm going to select my data, add a series, X values. I will choose values, I will choose 1 over the concentration of the reactant. And go ahead and add that. Fantastic. I'll bring it back down here. We analyze it and compare them. This was if we followed second order kinetics. And we have time in seconds. 1 over the concentration, dinitrogen pentaoxide. Here we go. And I'm going to add a trend line just to look at the equation. All right. So what we see here, so the whole point is when you plot the data, if you get a straight line, then that reactant is following that order of kinetics. And the way we can see that by analyzing the data is to look at the equation of the line and the R-squared value. The R-squared value tells you how good of a fit you have. We just performed linear regression analysis. And so you can see here that with 0 and second order kinetics, the line doesn't fit very well. And R squared's only 0.95. The closer you are to 1, the better your fit is. Now with the first order kinetics, R squared is equal to 1. So in this case here, dinitrogen pentoxide, when it's decomposing, it is following first order kinetics. Okay? And so whenever you're given data of a concentration of reactant and time, you need to plot that data to see whichever one gives you a straight line. And like I said, we're only studying in great detail 0, first, and second order kinetics, but there's all sorts of kinetics out there. You can have fractions as well. And so, you know, this is an example, like I said, we're just studying these specifically. Now, students will ask me, well, do I have to plot data for a quiz? No, you don't. But I will describe the data to you. So it's important that you understand, like, why is she describing what she's plotting on the y-axis and the x-axis? What is she trying to tell me here, right? So by practicing with this problem, you're kind of going forwards, you're doing a true kinetics experiment in a sense. But then on a quiz, you kind of have to work backwards because I'll have to describe the data to you and then you'll have to use that. You may not see the graph, but I tell you the equation of the line and I tell you what I plotted. And then you can look here and say, oh, she got a straight line with a positive slope when she plotted 1 over the concentration of the reactant versus time. She must be telling me that's second order kinetics. So there's your clue there, right? So you're always kind of looking for what clues are out there. Okay, cool. So for this one here, we're following first order kinetics. So that's what you're talking about here. And then it says calculate the value of the rate constant. Well, that's really easy. Once you realize it's first order kinetics, the slope is equal to the negative of the rate constant. And so even though it says, you know, y is equal to negative 0.0078x minus blah, 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 the y-intercept there, the rate constant you can extract out from the slope of a line, okay? And then it also already tells you what the units of the rate constant are, so that even makes it better. And then the last question's asking, what's the concentration of dinitrogen? This should be pentoxide. I told you I had a typo here. At 250 seconds, right? So the graph is giving you, you know, up to 200 seconds. But once you have like this data, you can extract out like, okay, what would happen, you know, what would be the concentration even beyond that? Well, remember that the integrated rate law allows us to determine the concentration of a reactant after a specific amount of time has passed. And so when you're asked like, well, what would be the concentration after a certain point in time? Then that would be the clue to use the integrated rate law, right? And so you would use, it doesn't matter which one, this one's just rearranged, right? But you would use the first order integrated rate law and you would plug in 250 seconds here. You know the rate constant now because you analyzed the data and you got the equation of the line. You know the initial concentration, that was right here, 1 molar at time is equal to 0. And therefore, you can figure out, what the concentration of the reactant would be after 250 seconds has passed. Okay? So that's what's cool about the integrated rate law. The rate law tells us the order with respect to the reactant as on the rate of the reaction, and the integrated rate law allows us to calculate, well, like how much is left over after a certain period of time has passed, right? But we couldn't have done part C without doing all this graphing and determining what kinetics was taking place first. Okay. I know this was a long video. There's a lot of information here. I'm so glad a student asked this question and I was able to go over it here. But if there's still any confusion, please don't hesitate to email me or visit my office hours or schedule a meeting with me. You guys are doing awesome. Keep up the hard work, and I look forward to chatting with you soon. Take care.